Hello, everyone. I'm Deep Medhi. I'm the organizer of the SKC Science and Technology Webinar series. Today, it's my pleasure to have Priyanka Das Rajkakati. She is, I know her for a long time. I think 2013 is when she first sent me an email. We have been in touch since then. She studied in India for her undergraduate and then a PhD in French. And she is in the very interesting space of, space exploration area that she has been very fascinated along with the art aspect of it. And so today she's going to talk about the precise navigation and art towards space exploration. And that is partly based on her PhD dissertation and more things she has done since then. So with that, I will hand it to you, Priyanka. Very glad to have you today.
Thanks, Deep. So I'm going to share my screen. Wait. Yeah, better this way. So you can see my screen, yes?
Yep, the screen is showing up. Everything is good. All right, take it away.
Good to go. So yeah, this because of this COVID pandemic situation, we were so dependent on webinars. We realized that today we are able to send humans to the ISS, and we've already sent them to the moon, and we are sending them back to the moon again because of the Artemis missions in a couple of years. And sometimes we still have problems with the internet, you know. so quite funny. So thank you, Deep, for inviting me for this talk, something which is quite close to my heart. So my PhD dissertation, because it took 3-4 years of my life to do it. And also during this time when I realized that there was one thing doing science mindlessly because it's exciting, because you get some returns, for your ego as a scientist, if you can solve an equation, if you can, publish a paper. But there was something lacking in terms of why you were actually doing science and what's the idea behind it and what is it actually doing in reality, like what's going on. Because a lot of times we hear the same argument that, even the atomic bomb was made by scientists. So that humanitarian aspect was something which has always been very important to me, because being from an Assamese background, I grew up in Delhi, but thanks to my parents, I was very involved with the Assamese cultural scene in Delhi, and culture and art has always been a part of my life. And it was not going to go away just because I did a PhD. So so this talk is going to be a bit about so 2 parts of my research. The first one is something I did at a lab in France on understanding GNSS navigation, and on the other side, what exactly is space exploration? Why are we doing it? Are we doing it properly? And how can art be a useful medium for answering these kind of questions? So I will start with the SKC webinar series itself. So Saurav Kumar Shaliha. And I discovered the link on the website, and then I didn't know his works before, but now I've started to read. It's quite interesting, actually. And something that really resonated with me in this description on the website is this line, every heartbeat causes a wound, and life would be a continuous bleeding to death if there was no narrative art. And here there are 2 things: art, so that's something I really love doing, and the part that you have to add a story to it, because we are not robots, even astronauts up there out in space, they are not robots either. And even though they might be the best of the best lot out there who are able to do hyperfocus, but as we continue through this lecture, I'll present you some cases where it's quite evident that art and adding your own personal story to it is something very important for us as human beings. And so as an icebreaker with the audience, I wanted to present this video, which is fantastic.
Yeah, I know that. Yeah, Mike Finke. So,
so I'll just play it. Oops. Sorry. So the first time I saw this, I was laughing so hard. So just for a bit of background, those who don't know, this is NASA astronaut Mike Fink, who in 2004 did Bihu in space. And why he did that is probably related to the fact that he's actually married to an Assamese lady, Renta Soikia, who also works at NASA. And this was a show of, this International Space Station is a great outcome of technology, a lot of minds coming together, a lot of cross-disciplinary research. Everything, you have to build a system, you have to build the electrical system behind you, and because of that, you have to build the thermal system, the power system. Then you have to do ergonomics because you want to put in humans there, you want them to feel, not lose their sanity in such a cramped space. And then so on one hand, you have this design research that goes into how you can make something like the ISS more ergonomic for astronauts. On the other hand, you have astronauts themselves, indulging in these kind of cultural activities with widespread. I mean, when this was showcased in Assam, I think people went sort of crazy. And so space just has this power of, inspiring people and connecting people actually from different backgrounds. And this one is also something I really like. It's a photo of the French astronaut Thomas Pesquet, who played his saxophone from space. And just to tell you, it costs something between 20,000 to 100,000 euros per kilogram for sending anything into space. And now, so when he was asked to send when he requested to send some personal objects with him, he decided to carry a huge instrument. So you can imagine how important this piece of art must have been for him. And
that's awesome, actually. That's very interesting. I didn't know that he took his saxophone to space,
Yeah, this is from this, I think this was showcased in this movie called 16 Sunrises. Says Levier de Soleil in French. Levier de Soleil in French. Yeah. So it's this is life on the ISS. And this is the cupola, which is the window on the ISS that is facing directly in the nadir direction, so downwards towards the Earth. And this is another image of the cupola, and this is something very personal to me because actually on this little gallery that you see is my own artwork. And
that's awesome.
And I always, as a kid, I always wanted to be an astronaut. The childhood dream can be at the same time very naive, and on the other hand can be very powerful to sort of make you decide things in your life to achieve that kind of goal. So I argued with myself that because I drew that piece of artwork by hand, I have a bit of my skin cell out in space now. So does that make me an astronaut? And so basically the point of this talk is to present two ways I did a bit of reflection, a bit of research into the space domain. So the first, the hard stuff, which is getting a PhD, which would gave me basically a bit of insight into what exactly does it mean to do research and go in depth into a particular subject. Because when you're just learning things at university, then a lot of the details get lost for the sake of being for time or for not having enough opportunities to go in depth. And the second part would be the more philosophical research into why I'm actually doing this and what does it bring to me apart from a few research papers and research papers in collaboration, that too with a laboratory. It's not like I came up with these equations overnight by myself. So a bit of background. So I grew up, I'm Ohomia. I grew up in Delhi, where I did my bachelor in physics from St. Stephen's. And then I went to France to pursue a sort of a double master. So it's a French degree called Ingénieur Polytechnicien. It's from this college, university, which is quite well known for mathematics, called École Polytechnique. And then while there, I found the opportunity of doing a 1 year at this institute called Supero, where I could pursue this. Initially, I thought, okay, being working in space meant you had to start with a bachelor in space science, etc. But it's no, you start with a bachelor in physics. It gives you a very general idea of everything, a lot of different phenomena that happen in our around us, and that then you can go a bit in depth and pursue it with higher studies. And it was during this time in 2013, while doing my bachelor's, when I reached out to Deep to say, hey, I'm doing all this physics, it's great, but can you tell me how I can, you know, have a structured understanding of computer science so I can create artwork?
I still have your email from 2013. I did respond to you, remember?
Yeah, it was. I was quite surprised to see someone reply to such an email like that. But thank you. It encouraged me to, you know, not be like, okay, this is useless and I should just concentrate on physics and live my life that way. So once I was doing my physics degree in France, so it was not just physics, it was like a bit of mathematics, a bit of computer science, a bit of art. So Polytechnique really means multidisciplinary, and it lives to its name. And during this time, I had the opportunity of going to NASA Jet Propulsion Laboratory. That red arrow is me. I was one of the youngest in the group at the time, so the least experienced. And this was during an event called Caltech Space Challenge, where we were studying how to, from A to Z of mission planning. So our mission was, you have this NASA ARM mission that is trying to, okay, you assume that it has already worked. It has grabbed an asteroid and put it into lunar orbit. Our project was to understand how you would plan everything from the orbit you design to what kind of astronauts you would send, what technology would you, how do you build the spacecraft to go to this asteroid in lunar orbit, and then basically do some in situ resource utilization, ISRU, and carry back some samples of the asteroid. And during this time, I realized that I was really young. I didn't know anything about research. And so I decided to do a PhD. And then I got this fantastic opportunity of doing a PhD at a company, an industrial contract, which is called CIFRE in France with Safran. And I continued working with a group at Supero to finish this PhD. So the PhD was, so I didn't know what, so I knew that satellite technology is used for calculating your position on your phone receiver, right? I had no idea how it's actually done. And so this PhD was kind of an opportunity to go a bit in depth into the basics, at least, of what is happening, and then try to go a bit in depth into the mathematical aspect of how this position is calculated, how can you make it more precise. And of course, I did not finish the PhD by making GPS precise to the nanometer, but I ended up by learning a lot of things about it.
So Priyanka, I have a couple of quick questions here. First is that maybe it might be good, maybe you are already planning to do that at a very high level, the distinction between GNSS and GPS, that would be good.
Yeah.
And maybe say something about what's the accuracy of GPS, current GPS, in terms of the, not, it's obviously not in nanometers, so that would be also useful to know.
Yeah. So first part of that question was my next step, which is GNSS stands for Global Navigation Satellite System. And at the global level, so global as in everyone on Earth can basically, if you have the right kind of receiver, you can have access to these signals. So GPS is something which everyone knows, global positioning system. It was developed by the US in about 1970s when they needed more precise systems. And just for your information, when we sent humans to the moon in 1969, there was no GPS. Everything was based on inertial navigation, which is incredible. And GPS has just made everything more precise. But there are other global level GNSS as well, such as Galileo, which is European. There is GLONASS, which is Russian, Beidou, which is Chinese. And then you have these regional level ones also. So India also has its own one. It's called the NSS, so Indian Regional Navigation Satellite System, or NAVIC. And apart from these systems, which is basically a constellation of satellites, you can also have augmentation systems which can be ground-based or space-based. So EGNOS in Europe, WAAS in USA, and SAS in Japan. Now, how does this work? So it's basically each of these systems at the global and regional level, they can be a constellation of about 18 to 30 medium Earth orbit satellites. Medium Earth orbit in the sense they are at an altitude of about 20,000 kilometers above the surface. In comparison, the radius of the Earth is about 6,400 kilometers. So you can see it's quite far away. And because they're covering the Earth, you can have access to a few satellites at the same time, which can help you calculate a position. How that is done is using this basic principle called trilateration. So you have two circles. So when you intersect two circles, you have 2 points. But to precisely determine which one is your correct solution, you need a third circle. And it's basically a system of linear equations, if you may, where you have 3 unknown variables, x, y, z. And so you need to have 3 equations that are independent to solve this equation. And this is in 2 dimensions, but in 3 dimensions out in space, so you don't have circles, you have spheres. And how these spheres are made is by the antenna, which is propagating the signal in 3D space. Now the intersection of 2 spheres is a circle, not 2 points. So because of this, you need actually a 4th satellite to precisely determine your position. But you can get away with that because at the end, when you have only 2 points left, you can say, okay, one solution is on Earth, one is in space, so we can discard it. So technically, you can do it with only 3 satellites. And then you find your position. And so basically the distance is, what is this distance that you're using? It's basically, what is the distance covered by the electromagnetic radiation, which is the signal that you're detecting on your receiver. It's an electromagnetic signal, so it's traveling at the speed of light. And if you can precisely calculate the distance between the satellite at the time it was emitted and the time that signal was received by the receiver, you can calculate the distance that has traveled. And that gives you basically the radius of these circles. And you can solve your equation, you can calculate your position. But in the real world...
One quick question here. In this particular situation, even the Earth is also rotating, obviously at a pace.
Yeah.
And then you have satellites are also moving at a slightly different pace than the Earth. So how do they connect together?
So actually, this is a real world situation in which you're just assuming everything is static. But you're right, in the real world, there is a lot of corrections that you have to add. So this R is actually called a pseudo range. So a lot of these error sources, not just exactly error sources, but corrections you have to add because the Earth is rotating. There are also relativistic effects because of the gravity of the Earth. So I don't know if you know this, but okay, I don't remember the exact figure, but satellites who are at 20,000 kilometers altitude, they travel at a completely different sense of time itself, and you have to also correct for it. But because you're closer, because they're also moving really fast. So because of special relativity, time dilation happens, and for them, the perceived time is slower. But for us, because we are closer to the center of the Earth, the gravitational force is even stronger. So for us, time is dilated because of general relativity. So this is like special relativity and general relativity acting at the same time, which means that you have to correct for something like, I think, around 45 microseconds every day for these for this. So these corrections and error sources mean that this distance you're calculating is just a pseudo range. And I'm using the word calculate, but it's actually wrong. It's estimation, because of these error sources, you are going to have all these equations that you're going to solve, and then you're going to estimate this position. And what you're estimating here is basically this time difference called the time delay, where the satellite leaves, the satellite signal leaves the satellite and is received on the Earth. And it's called a multilateration problem. So you need to have a minimum of 4 satellites. Remember, I said you need a minimum of 3 satellites. But because now you have this error term also, which you have to estimate, you need to have a minimum of 4 satellites to estimate your position. So now, how does that actually happen? So what does this GNSS signal structure look like? So on the right-hand side, these are, at least of the time of making this graph, it was all the satellite constellations that are there. And you can see these patches. So they are basically on the x-axis, you have the frequency on which they are modulated. So I'll come back to that in a bit, what that actually means. And you can see that they're all patches of signal. So that's something called a band limited signal in the frequency spectrum. Now, on the left side, I gave an example of what the GPS L1 CA course acquisition signal, which is basically the open signal that everyone has access to, looks like. So the transmitted signal can look like some very random electromagnetic curve, but it's actually made of about 3 subsections. So one navigation message, which is the one which is used for giving you a global idea of how far the satellite is from your receiver. Then you have the PRN code that helps you to, that is transmitted to tell you which satellite are you actually tracking at what time. It has all the time data. And then, because these electromagnetic signals, for example, right now I'm speaking to you on mic, so you can hear me thousands of kilometers away. But if you were standing right next to me, if you move further away from me, you'd hear my voice, wavering and losing intensity. Same thing happens with electromagnetic radiation, actually, because of it gets dispersed or it gets attenuated. So to stop that from happening, these signals are modulated onto an extremely high frequency signal called the carrier wave. And the carrier wave basically shifts it in the frequency spectrum. I'll come to that in a bit, what it means. And so on the right-hand side, all of these different GNSS frequency bands sort of show in what frequency spectrum it's being emitted, and most of them lie between 1 to 2 gigahertz of frequency. So a quick note on something called Fourier Transforms. It's something, when I first started studying it, it used to scare me as a student. But then once I got into it, it's a very beautiful theory of how, when you have a signal in the time domain, so when a regular equation, say you have x as s as a function of time, this you can actually decompose into a set of weighted sums of sinusoidal curves. So that is the Fourier transform. And here in this image, you can see, I don't know if I can use a pointer. Yeah, I think.
Yes, I can see the pointer. Yeah. Yep.
So here you can see that it's just a curve in the time domain, which is composed of, 2 sinusoids. And this is what you would probably see on a CRO if a cathode ray oscilloscope. But this one can be decomposed into the 2 sinusoids that compose it. And then here in the frequency domain, you see what is the frequency, or the omega of, like, sine is cos omega is a sine equation. So what is the omega, value of the omega for that particular frequency division? And so this is a very simple example, but you can have very complicated curves, which can more or less be all, represented by at least some sort of approximation of a Fourier transform. And why are Fourier transforms interesting? It's because mathematically, they're very easy to handle. For example, what you're trying to multiply in the time domain is just an addition in the frequency domain, that kind of thing. And more complex your signal is, the more difficult it gets to actually, so you have this GNS signal that is composed of so many different signals. How do you actually separate those quantities? So in that case, this is where Fourier transforms come in.
So quick question here, Priyanka, in the context of GNSS, maybe you'll talk about it. Why separating out is important to the different.
So I'll be coming to that in the next slide. So here I was just a quick animation of what is actually happening in the transmission and reception chain. So here you have the satellite, and then you have the receiver. So what is happening within the satellite block is, you have this first time series, which is the code, the navigation code or the PRN code that you want to modulate onto the signal is generated. Then it goes, basically becomes, so these are just points, but you want to convert it into like a real signal. So you do a digital to analog conversion. And on top, this is what the signal looks like, and this is its frequency distribution. So these points are basically now this. And then you do something called filtering, where you remember how I showed you in the previous diagram, all of those signals in the frequency domain, they seem to be limited in bands. It's so that once you recover the signal on your receiver, you don't have to deal with a huge spectrum of information. You can just concentrate yourself, oh, okay, I know the GPS L1 signal belongs to this band, so I can just treat it in those frequencies. So computationally also it's nicer. So the band limited, the filtering basically limits this band, and you have something which is smaller. And then it is modulated onto the carrier wave. So as a property of the Fourier transform, you have this negative frequencies and the positive frequency just gets gated. And this distance is basically the value of the carrier wave frequency. And then it gets transmitted on the receiver end. And then in the receiver, you see that what you transmitted, because of the accumulation of all the error, it's not exactly this exact same curve as what you saw earlier. There was a lot of noise that got added. So first, what you do is you demodulate it. So you first try to remove as much as possible the carrier frequency. And then you do some treatment so that you have this an analog signal that you have, but now you want to recover the digital version of the signal. And here's something called the Nyquist-Shannon sampling theorem. So basically, it's an electrical signal which is sampled at a certain rate when you're receiving it. So the receiver has this timestamp. So at this timestamp, I receive this kind of amplitude at this timestamp. So it's a sampled signal. And the Nyquist-Shannon theorem basically tells you that the sampling frequency just has to be at least greater than twice the bandwidth, so that you can recover the entire, you can recover the whole information that is being transmitted. And okay, this might seem like a lot of jargon, but this has some other applications that you also use in everyday life, which is MP3. So you have this analog, when you're playing a vinyl record, it's an analog sound because it's following the grooves. But then when you make it into a digital sound, you can lose a lot of that information. So your sound basically your music has to be sampled at a minimum of 44.1 kilohertz. Why that? Because the maximum hearing range of a human ear is 22 kilohertz. And so basically it has to be slightly greater than twice of that. So this is where the 44.1 kilohertz that you must have seen comes from. And then you use something called a Hilbert filter for extracting this baseband signal. And finally, what you send, and this is how it gets comes back to you. And now it's up to you to treat it so that you can recover as much of the information as you can.
So this is really great. I mean, the other important thing about this whole thing is that the entire idea actually sits on the shoulders of giants, basically. You know, if you think about it that way, because many people have done work from physics to communication theory to, you know, to Nyquist work, you know, to be able to really get to where it is today. You know, so I think it looks simple when you look at that. Oh, I know where I am, but it's actually worked for long time, you know. And so
that, and what I always find fascinating is how you can use something someone might have come up with as a solution for one particular problem, and you use it for something else altogether.
That's correct.
Something like, just okay, won't divert too much, but I just got reminded that there's something about this Fourier transform that I really loved from the point of view of an artist, is when I did this internship for creating digital holograms. And turns out for reconstructing, so if you've studied optics, you would have heard of something called the Fraunhofer diffraction equation and the Fresnel equation, that kind of stuff. And turns out the Fraunhofer equation has the exact same form as an inverse Fourier transform. So people use this to sort of, okay, you have interference of light creating a pattern, and then when you record that pattern as a digital signal, like as just pixels or whatever intensity map, you can apply your inverse Fourier transform to it to recover your old image. You know, so for me it was wow, that, you know, you have all this transdisciplinary, even within science.
The Fourier transform is incredible in that way. How many different ways, you know, that's been used in many different spaces. I want to make one, I don't mean to deviate from what you're talking. I want to make one quick comment. You talked about your, you know, 44.1 kilohertz, and then human ears can hear up to 22 kilohertz. I wanted to tell one thing, that the band was a very expensive idea when the telephone came out many years ago. And so what they did is that they capped it only at 4 kilohertz. So anything higher than 4 kilohertz, you actually cannot, because you cannot hear. And that's why the letter P and letter B, you cannot hear very well on the phone. Then you have to repeat it, you know, with a word like a Paul or boy or something like that. So the other side. And that's precisely because they didn't have enough bands to be able to send as many calls. So they said, okay, we're going to do a trade-off, really. Trade-off was basically saying that we're going to only use 4 kilohertz to, you know, be able to communicate, because most people can understand, unless you're spelling a letter or something, just telling a letter, that most people can understand what we're talking about. So just wanted to give the context to that. And that went into digital signal for the phone call. It became very interesting, the sampling thing that Priyanka talked about actually came up again. So sorry, I didn't mean to do, you know.
No, it was very interesting trivia. I mean, not trivia, trivia from an old timer was very important.
Exactly.
I think our generation is just too used to this conversion happening, you know.
Right.
And so for me as a young researcher, it's quite interesting to study these kind of reasonings, and I learned something new. Thanks to you. Thanks. So next part is what I was trying to study through my PhD. This is GNSS error sources. So if you remember from the previous slide, so this is the signal you wanted to transmit, and this is what we actually receive. This is because a list of different kinds of error sources and corrections. So there's the clock offset, which can go up to 100 kilometers. You have the clock corrections of the order of meters, and etc. And just to give you an appreciation, so Deep, you asked what is the accuracy of GPS. So for the L1CA, I think it's about close to a meter. And but if you use different frequencies, for example, the P code or some other kind of code, you can go even lower to let's say. But those are not available for the general public.
Correct. Right.
So actually, GPS has a very interesting history because initially it was not really. You had something called so the CA, course acquisition code, was actually they added noise to it so that, I don't know, Russia would not use it, for example. And this actually caused a plane accident that could have been avoided. And that's when they got rid of this extra noise that they added. And now basically everyone can use it for getting a few meters of accuracy.
Yeah, talking about noise, when I was traveling in China, if I look at the map and where I am, it is actually off by. And then when I come back to the US, everything is okay. I look at my information of walking and tracking myself on a Runkeeper. That was quite interesting for me. So,
yeah, that's actually a fault of, not a fault, but that's the receiver by design. In China, GPS does, I think it's by design not supposed to be very accurate.
Correct. Right. So they're kind of
but the satellite is still emitting whatever it can. It's the receivers that are programmed to do that. And so just to give an idea to the audience why I'm talking about these few meters of error. So the GPS signal or GNSS signal, it's an electromagnetic signal. You multiply it with the speed of light to some, say, corrective factor because of ionosphere and all that. So even if you have a 1 microsecond error, 10 to the minus 6 of error, you multiply that by the speed of light, that's already 300 meters. So that's why this is an estimation problem, and this is where all this mathematics comes into play, because the theory of this estimation comes into place so that you can keep improving your estimation methods so you can reduce this error. And now already if we have a few meters of accuracy, it's quite incredible that you have this huge system 20,000 kilometers away who's sending that little signal that is spread all across the globe, and you only receive like a tiny part of that on your receiver, and you're still able to calculate a position. For me, it was like incredible to study this system. It's like, for me, it's a beautiful feat of human achievement. So next. So this is where I would like to go into the time delay. So time delay is what we're trying to estimate, which is how much time does the signal take from going from this receiver, from the satellite onto the receiver. And because the Earth is moving, because the satellite's moving, there is something called a Doppler effect that gets added. So Doppler effect is, for those, I'm guessing everyone is in the audience would be aware of it, but when you're hearing, when you hear a police van coming towards you, the sound seems really sharp and high-pitched because it's all that sound getting compressed. And when it goes away from you, it's getting dilated, so just the pitch just goes down. Same thing happens with light. When you have something moving towards you and it's also emitting a light, the frequency of that light just seems to increase. And when it's moving away from you, and the frequency goes down. And this thing is also used in astronomy. It's called the red shift or the blue shift for calculating how fast a galaxy is moving away from ours, for example. And in GPS also and GNSS, this is also very important, this Doppler estimation. And so this is a question which Deep, you were asking. So why is it important to separate these signals from the main signal that you receive? So if you remember at the beginning, I had said to calculate your position, you basically need to know the timestamp when the signal had left and when it was received. And this information is related to you through several of these messages that are modulated onto the carrier phase. But if you look at what is physically happening, you have this antenna of your receiver. It's not going to receive a thing saying, oh, okay, it's this precise signal which has, at this point, this part belongs to the message, this part belongs to the code, this part belongs to just the noise. At that point, it's basically the sum of all the signals. It's just the value of an intensity of the power which is receiving. And what you have is just a time series of the sum of all of these signals. And from that, you're expected to decode what each of the values of these signals could be. So when I first thought about this, I was like mind blown because I couldn't understand how we could actually do something like this. But turns out there are very beautiful theories in estimation that help you to do this precise thing. And this is what is being done in your receiver end to extract your position. And not just position, but also velocity and a ton of other information that you can extract, even your date and time. So GPS is also used as a very accurate way for synchronizing atomic clocks across the world, for example. And this timestamp on the GPS itself is very precise because there are atomic clocks placed in the GPS itself. So a solution is to use a sensible form of the signal code. So you use something called the pseudo-orthogonal code. So basically what happens is if you have a signal like this, such a way that if you have two different satellites emitting their own unique PRN codes, and even if they have a sum, they are emitted in such a way that you only receive a high power output. Basically, there is a correlation when you are matching it in your receiver with that precise satellite. So if you have something called a replica on your receiver, and it's constantly going through this time delay and Doppler field to see, okay, this particular signal has come, and so which one is it? So it tries to match it, something called a matched filter. And in that match filter, the moment it slides and it correlates with that precise signal signature from that precise satellite, that's when you have a positive output. And here you can see that in all this mess, the receiver is able to decode that it has found these 4 particular satellites with a particular PRN code.
Mm-hmm. I mean, that's what is incredible in that sense.
Yeah.
You know, being able to distinguish it. Okay, which one is actually talking? You know, it's like we're in a crowded room and we know that, okay, I'm talking or Priyanka is talking, although we're actually talking at the same time. That's really what this is equivalent to, you know, right? So
yeah. So in your brain, you have a matched filter that knows the signature of someone's voice.
Mm-hmm,
and then when you hear a lot of noise, then your brain tries to match that signature in that time series information that you have with whose voice can it be. So it's a very good analogy, actually.
Mm-hmm,
so thanks for that. I'll use it for my next talk on my PhD. Yeah, but that's how it happens. So you have this huge mess of signal that you receive at your antenna. And then you basically do this correlation, and then you are able to detect the signals. So this is actually called the synchronization problem. And like I keep saying, it's an estimation problem. It's not a calculation, or you determine the position, you don't calculate it. And so it's something called a maximum likelihood estimator. So an estimator, because it's an estimation problem. And what it's doing is, so you have this space, very simply, to explain it very simply. So here, this is called the ambiguity function, in which you're going to do your matching. So what happens is, say one of the axes is time and the other axis is the Doppler shift. And so what the estimator does is, it tries to go in, in sections like this till it finds a perfect match to within a certain error area. But because it's an pseudo-orthogonal code, this perfect match basically shoots up at that precise point. So at this point, you know that the time delay for that particular satellite is this value, and it's probably Doppler shifted by this much value. And then you can use that for correcting the signal, and you can extract it. And then you apply your models for, say, what might have been your ionospheric correction at that point in time. Was it different kinds of information that you can extract from, say, your, like I said, you don't just have these global systems of satellites, you also have these augmentation systems which can provide you with additional input that you can use for reducing the size of this this peak, so that it basically gives you that one sharp peak that you can use for calculating your position. And you do this for every single satellite, and then you have this time delay for every single one. You multiply the speed of light, you get your the distance, and then you do that thing in the beginning I showed, where you have circles intersecting, and then you find your position. And so, because it's an estimation problem, there is a fundamental question that comes: how precisely can you estimate it, and what is the ultimate achievable performance that you can achieve? And this is where my PhD came in. And so, because we are using a maximum likelihood estimator, there are different ways of trying to see how good an estimator is. We use something called the mean square error. It's a very standard way of finding how closely two curves relate to each other, basically. And it's quite a useful thing, because it's continuous, it's differentiable, and it gives you a very good measure of this maximum likelihood estimator. And so the solution for this is the solution to this synchronization problem of finding out what is the ultimate achievable performance is to understand. So this mean square error is basically, I'll show in the next slide. It's like the sum of squares, basically, and you're trying to see what is the minimum of the sum of the squares that you can achieve. And that gives you a lower bound on this mean square error. So a little tribute to Mr. C.R. Rao, Professor C.R. Rao, who was born in 1920, and I think is still alive.
I think so. He's still alive.
101 years old. So I think statistics is a very good field if you want to live. And so I love this quote of his, which says, if chance is the antithesis of law, then we need to discover the laws of chance. And this is the basis of statistics and estimation. And this is what the Kramer-Rao lower bound is based on. So the CR, okay. Yeah, so the CRLB is, or the Kramer-Rao lower bound, is just one lower bound that you can use for studying how precisely you can go down to estimating your mean square error. So what does it actually mean? So I'll try to be as simple as I can. So let's say you have a signal. So in our case, the GPS signal, some time equation, say S of t, where t is that instant of time, which contains this parameter theta that you want to estimate. So theta here, for a simple case, is the time delay that we want to estimate. Now, and this theta is contained in that signal S. So your estimator, basically theta, and this is the symbol for an estimator, and you use an unbiased one, which basically means that over time, if you take enough of these samples and then you find the average value, it will more or less converge towards the value of theta without any bias. So that's an unbiased estimator. Now, for such a signal, you have something called a Fisher information matrix, F theta, which basically quantifies all the information you can have about this particular equation, so of the distribution. So it's because it's, so here what I should mention is I'm dealing with Gaussian noise. So all the noise that is being added, I'm assuming it's Gaussian. So this Fisher information, it basically tells you everything that you can possibly know about the signal. And then when you find the inverse of that, it gives you the equation for the covariance. So covariance is how far are you from the actually the true value. And so if you are able to minimize this covariance, that means it's the best possible estimate you can have for that particular problem. And why is it interesting? It's because it's quite easy to calculate, easier than other lower bounds. And it also gives a very accurate estimation of this mean square error of the maximum likelihood estimator, which I just showed you, under certain conditions. For example, very high signal to noise ratio and a large sample space. And what the Kramerau lower bound basically says is, if you take this equation, if you differentiate the log of this likelihood function, where x is the signal, it should have been s and not x, I'm sorry, which is trying to estimate this theta. This log likelihood, if you are able to write it in this form, then basically whatever your equation, if you're able to reduce it into this form, then whatever term you get here is the value of this Fisher information matrix. And then this thing here would just be the value and the value of the covariance that you have. And so here, so just to give you an example, if you want to say you want to measure DC noise, and so you have an equation such as the signal at a time instant t is the value, that constant value theta of the DC voltage plus some additive Gaussian noise. And because it's an additive Gaussian noise, it follows the law of the Gaussian. So here the P is basically that Gaussian law. And so when you find this, the log of P, and then you differentiate what you're trying to estimate, which is the value itself, which is a constant, what you'll find here is F will just be the value, here F is just going to be the covariance, which is n over sigma squared, which is the value of the covariance of this problem. And g of x here would just be the value of the Fisher of the estimator that you're trying to see. So in this case, okay, to put it in simpler terms, what exactly is happening is you have a DC voltage. So by instinct, to find its value, what you're going to do is you're going to take n samples, say 100 samples, and then you're just going to find its average value over those n samples. And the higher the number of the value of n, the closer you get towards the true value of the DC voltage. So here in g of x, you will see that this is the value that comes. And I think I hid the slide basically, which shows that, but we can come back to it another time. So the Kramerau lower bound is basically, this is how it's calculated. You find the probability distribution, you find its log likelihood, and then you differentiate it with respect to the parameter you're trying to estimate. And then you extract the Fisher information matrix, and then you also get a value of this covariance. And it kind of makes sense here because minimum covariance basically means you're deviating from the true value that much. Now, anything that is greater than the inverse of this Fisher information matrix basically means that you have less information of that particular situation. So if the Fisher information matrix gives you all the information, then its inverse should be the smallest possible, right? And so that is what is being reflected here, that the inverse of this Fisher information matrix, you have to minimize it so that you can achieve the maximum performing bound. If anyone has any questions.
No, that's very, very well explained, and very complicated things related to connecting between maximum likelihood principle, Kramerau bounds, and the Fisher information matrix. Very good job. Yeah.
I will go back in time and show myself this video.
Yes. That's why we're recording it. So yeah.
So yeah, so this, yeah, go ahead.
That's what you use it for your dissertation work, to use the Kramer-Rao bound. But
Yes.
I have another quick question. That you said the Kramer-Rao bound is CRLB is easier to calculate, and that's why it is used. And so obviously the intent of the being easier is that because you're trying to do it in a very short amount of time. That's what the intent of the easier means, right? So
yeah.
So I guess more of a trade-off question to you, Priyanka, is that, if you can do what could be a rather a speculative question to you, that if you could do if you can get a more precise bound on it, and if you that takes more amount of time to calculate, what would be the implication of that in terms of the accuracy in the distance that you are trying to achieve? Because you have to, it's almost like Heisenberg's principle, right? You cannot have, so you cannot have all things together at the same time. So you are always going to make a trade-off there. So
yeah, so the trade-off here was, so this was the next, so basically it depends on the signal model you're trying to study. So in our case, so the signal model which we used was under very certain conditions. So
correct.
If I can go to the next slide, maybe it'll be. So before I go to that, I'll just finish this little slide on. So tips for visualizing equations, because people tend to get very scared of them. So here is a sine into exponential curve.
Right.
That is quite, has been quite pivotal in all the equations that we study in signal processing. So this is what it looks like. And I tried to adapt it to my situation, which was, so it's basically showing you how your motivation level fluctuates while doing a PhD.
That's a good analogy. So
like you said, trade-off. So when you have little gain, your satisfaction level wavers a little bit. But if you're able to, if you continue, going further and further, and this trade-off is basically between how depressed are you willing to be, so that the next step takes you a bit higher. And then, of course, this is with time. And if then a global pandemic happens, then it's not so nice. But then the important point is like to always try to find yourself at the top at the end of it. So this was my tip for, making things personalized to you. At least that's how I work.
Great.
And so this brings me to the GNSS case and why Kramer-Rao bound. So firstly, the key assumption that is to be highlighted here is that we're dealing with band-limited signals. And yeah, so we're dealing with band-limited signals. And this CRB basically gives you a very interesting so this CRB for the kind of signal we were studying is actually quite useful, and you cannot really go much better than that. Of course, you have very low signal to noise ratio, and you're dealing with say in the case of GPS, if you're dealing with something like signals bouncing off buildings and coming towards you, or if you have different kind of noise that keeps getting added, then that is a different problem that I didn't attack during my PhD. So I was looking at a real world scenario where everything works fine. You have a little bit of noise being added from the ionosphere. So the question was, why did we deal with such a simple signal example in the beginning? Because that's how it's interesting to start, to at least try to understand and characterize the simplest situation that is out there. And so we considered GPS signals at very high signal to noise ratio and very large number of samples. And already we saw that there was a lack of delay, Doppler, and phase CRB, which was sufficiently generalized and easy to use in the GNSS case. And the magic words for this PhD was compact and closed form. Basically, I had this analytical form that was quite complicated, but it was not simple enough that you could calculate on your computer using MATLAB or something. And so we tried to see if we could characterize it if we could, solve the equation in such a way that we come up into something which is easier to solve, say in the form of a matrix, in the form of a sparse matrix, if possible, so that it's computationally very easy to solve, and then you can characterize if that estimation that you're doing makes sense, if it's doing its job properly or not. And then we also, staying in this kind of idealistic world situation, we also tried to see that already there was a lack of comprehensive performance analysis for this entire band of GNSS signals that exist. And so basically people were just coming up with different ways of creating different signals, but why are they doing that? Is it efficient at all? And then, of course, the basic problem. So this is where the question precise comes in precise navigation. So the signal that I showed, it has a navigation message modulated onto the carrier phase. It has the code message onto it. And all of these, basically, if you solve it, give you a precision of the order of a few meters. But if you were to detect the phase of the carrier phase itself, which is 1,000 times more precise or more energetic, and say you have this sinusoid that you are able to determine precisely, okay, this is where the timestamp starts and this is where the timestamp ends. You have way more information in the middle. So at the end of the day, estimation is just an information game, right? The more information you have, the more precise your estimation. So here what happens is, there was absolutely nothing in literature about, what would happen if you were to use GNSS phase itself, the phase of the signal itself for calculating. And while doing this analysis, it was in parallel in our lab. So I didn't directly do it, but the results we saw was that it's complicated. It's quite complicated to extract just the phase information, plus doing it, because I suppose that if tomorrow the person who's designing these GNSS systems comes up with a way to timestamp the phase itself, it'll make life very easy. But until then, we have to find the best solution we can as end users. And so if you don't want to use this phase of the signal, then the question comes, is it possible to just use the code itself? And how precise can you actually go by using just that? Under which conditions and with what kind of signals? So you have these hybrid signals that are also being proposed, such as the ALT-BOC. And you also have this problem of, not problem, but you have this one kind of solution which uses several constellations at the same time. So you have more information. So instead of having access to just 4 to 5 satellites per constellation at a given time, you also have 4 to 5 from other satellites. So you have 10 satellites giving you information. So all of this combined, how precise can you actually get? And you start off with an idealistic world situation. And so that's why we were dealing with Kramer outbound.
Great.
But there are other people in the lab. For example, here we're just talking about deterministic estimation, right? So deterministic in the sense, okay, I know that the time delays is going to be in this much chunk. It's not like a random variable. But there are people who are studying what would happen if you take it as a Bayesian case, where the thing you're trying to estimate itself is a random variable. Does that improve your thing? So that is also giving a lot of different kinds of interesting results. It can. So was I clear?
Yeah, very good. So are you going to talk about art part? I'm so curious about the art part.
Oh yeah, the time.
Don't forget.
So,
don't drift in time. You know, that's what you work on precision. So, okay.
So I will just quickly present in the next 2-3 minutes what the PhD actually did. So we came up with this. So no equations here, except this one, in which we proposed. So F here is this Fisher information. So epsilon here is the quantity you're trying to estimate. Deterministic quantities that you're trying to estimate. And so here tau, the time delay, knowing these deterministic parameters, we found that you can actually reduce it into a very simple equation in terms of just the signal to noise ratio, the maximum one at the output of the antenna, multiplied by these terms, which are just in terms of square matrices. There's no dependence. So we are trying to estimate something of about the time delay, but there is no mention of the of tau in the final product. So basically, it's an equation where for any random kind, any generic band limited signal, in terms of just the signal samples itself, and which does not even depend on the parameters that you're trying to estimate. So that was an interesting result, which was published. And for a real valued signal, it's even simpler. And here we see that you can also use these equations for finding a performance loss metric, where this factor D is just the largest eigenvalue in one of those matrices. And it tells you that if you design your signal in such a way that you keep increasing the length of the band limited signal. So here, what that means is, what is the length of the code which you're trying to correlate in time? If you increase that length, then of course, in one hand, it makes sense, because the more information you have, the better your estimation. And turns out here, where it's almost like 95 to 99% close, the value is 100. But if you look at it, the GPS L1 signal, that N, actually the value is 1023. So it's a huge signal. So it'll be somewhere here, which means that it's already quite close to how precise you can get with that kind of information. And we also sort of try to see if you can apply this to a lunar GNSS case, in which, so these satellites, they have this these bands, but then if they are so far that if you were to consider the part of the band that is not just going to the Earth, but is actually extending it, you might eventually even detect it on the moon, but the signal to noise ratio will be extremely bad.
Mm-hmm. Mm-hmm.
So in that case, how does that change your model, and what kind of receivers would you need? So
very interesting.
And we did find that maybe you could find a precision of the order of, like, say, a few hundred kilometers. A few hundred kilometers is okay, because that way you at least know if you're in the north or south of the moon.
Exactly. Right. That's good enough for that. Yeah.
Yeah.
Right.
And then after that, you can use vision-based navigation or something to more precisely locate yourself.
Yeah, I mean, then the next lunar expedition, that's going to depend on that, as opposed to 1969, right? When you had nothing. So that's why it was so incredible what they did, you know.
Yeah, with just inertial navigation. Okay. And just one trivia for people listening in. So the moon is not like the Earth in many ways. And one prominent way is it does not have a uniform gravitational field. Like the Earth has more or less a uniform thing. So you can have circular orbits around it, for example. On the moon, you have these mass chunks called, I forgot the exact term, sorry, but they have these huge gravitational chunks that distort gravity around it. So you actually don't have stable orbits around the moon close to it, except for like a few things called frozen orbits, etc. And the problem here is that means you cannot deploy GNSS constellation around the moon like you can do around the Earth.
Oh, that's very interesting. That's right.
Yeah.
Yeah.
So they're called mass cons. I just remember mass concentrations, mass cons. So that's why you have to resort to, say, elliptical orbits, or you have these non-rectilinear halo orbits that you can use.
So it brings
Which means,
additional challenges,
yeah,
even for.
Yeah. So for just 100-kilometer of precision, might as well just use a Earth-based GNSS system,
Okay, very interesting. Okay. So if you can send it up there, great.
Yeah. So now we come to the art part, and I found GNSS signals can be very aesthetic. So it was very nice to find something else to do with my time. And this brings me to the second part, which is, okay, you do all these equations, you spend a lot of time building technologies. To what end? Okay, you can say space exploration is important, etc. But is it serving only a certain kind of subset of humanity? So the first question is, why even pursue space exploration if you're not, say, from the US, and or Philippines has a space exploration agency now, for example. So what is the point of it? So one argument is that all this human resource you're developing for, say, doing PhDs or building technology, these can be used for workforce development also, and that can also lead to a positive growth for the country, and then back to money for research. So it's like a positive feedback loop. And that's one argument. And on top of that, all this technology, it's not just for using in space. For example, food that astronauts use can be used for disaster management solutions on Earth.
That's
and,
right.
So many Earth technologies that are used in space are used every day. Like I think
Teflon is one of them.
And then astronaut shoes also get I think the base of that technology is what inspired sneakers from Adidas. So you're using all of these technologies that are built in space, even microgravity experiments these days for doing cancer research, that kind of stuff. It's quite interesting. But then we can keep exploring. But then one thing that I did cause me a lot of discomfort was how people are just building and not cleaning, So there's a lot of, this is an actual, okay, it's an exaggerated version, but it tells you how space debris, is currently in space. And so we have to be a bit real, we cannot just keep building. We also have to build a way to clean all of this around us. And someone once said that, you're using low Earth orbit as a dustbin for all these satellites. And someone argued to that, saying a dustbin is actually a place where you collect junk. This is just, you're not even collecting, it's just out there in space. It's just basically littering and not collecting in a dustbin. So I feel being part of the space industry for so far, the way I've seen, a lot of these investment projects, a lot of projects that get all the money, projects that don't get the money, there is more focus towards a capitalistic part of space and less towards, sustainability. And so as an artist, I'm really interested in this kind of a problem. So if anyone in the audience wants to have a conversation about it, hit me up today or even later, can send me an email. And another thing that also I notice in the space industry is how there's this lack of diversity, even say amongst astronauts. There's a very specific subset, but tomorrow if you want to send humans on to space, you're not going to select the most hatta people, like not the best of the best lot. You're going to send average people, and for that you need to have data on the average person. And the average person is not just a white man from America. And you also need to have data on women. So there's this push towards diversity in space, which is going to become very important. And then also, this is something which, as an Indian living abroad, I find quite interesting, is how we can learn from ancient traditions of other cultures already. For example, in Asia itself, you have all these architectural techniques that can be used. India has a huge vegetarian recipe book that can be used for sustainable nutrition in space. All these nomadic tribes, they have survival techniques that one can learn from, and of course meditation, yoga from India for keeping a sanity check on oneself. And a lot of these so I had this experience of doing this analog astronaut training once in Hawaii, and there I was with 5 other people, and I basically taught them how you can save water by taking bath from a bucket, instead of using just the shower. So that kind of thing. And a lot of these questions that you don't learn in school or in college or during your education, that you have to learn through experience by doing a lot of these projects on the side. It kind of what drove me deeper and deeper into the cultural aspect of space. And so this is an example of how there's art in space currently on the moon. It's called Fallen Astronaut, for sort of talking about all the astronauts who perished for the sake of space exploration. It was taken there by Apollo 15 in 1971. So yeah, Apollo 11 is not the only mission to the moon. There have been 12 people who have walked on the moon, actually, all men and all American. So the idea was going back to this moon gallery. We want to change this, this plate a bit. We want to send more ideas to the moon about humanity, and each of these contributions here in this gallery is basically an artist talking about some part about humanity on Earth, and this how culture is very important for reminding us that it's not just about a capitalistic take on space exploration, but we also, we're going to build a community there, then we have to take ourselves there as a human civilization, not just as, as cold-blooded scientists or something. So these kind of art projects this is why I got involved with a lot of these art projects as well, so that I have, I try to give some meaning to the kind of work I was doing. And yeah.
Very nice.
And so this, I'm going to end the talk soon by just sharing, this is what my artwork actually looks like. So it's made by hand. It's very tiny. It fits in 1 centimeter cube. And so it's got this physical element as well. And also it has this chip, which contains these equations that I had been developing while I was starting to learn programming as a child, actually. And then they are equations of the most basic kind of movement in the universe. But if you change the parameters a bit, these are called hypertoroids. So if you change the parameters, you can get these intricate curves. And for me, it was like, wow, I can explore as an artist.
Very interesting.
So to end again with this paragraph from Saurav Kumar Shaliha, so I think art is very important, not just art, but also narrative art. So you can give a story to what you're doing, because without these stories, I feel one tends to get lost, and I have to learn maybe deep. We've been having regular conversations. But
I think the whole idea of when you work on a domain of space, the whole idea of space exploration definitely brings a philosophical context to it. What we're doing, where are we doing it? Where do you want to go with it? There's a scientific element to it, obviously, from a perspective. There's a design aspect, but what I find it fascinating for what you're looking at is that somehow these interesting things related to the mathematical equation and stuff like that, you could create this sort of a very fascinating art, because of the way you look at the signals and stuff like that. I guess it's mostly digital, or most of it, but it's kind of very interesting way to look at it that gives a context in the in the sense of space, I think so. And so that's very, very interesting for me. So any parting thoughts? By the way, if anybody in the audience have any question, you can unmute yourself and ask a question. I know you have a small audience, so there's time for somebody to ask question. We have a few more minutes, right, Priyanka? So
Yeah, I'm available. And
Okay.
by the way, just thank you for inviting me for this talk. And if anyone is interested, can follow my work on my website, or I'm on these social. I'm starting to come back on these social media, like Instagram. Yeah.
Any questions from anyone? All right. Okay.
So maybe I could ask you one question. So
yeah.
So what drove you to have these lecture series?
Very interesting thing, right? So I guess this is a good question. So as you know, I grew up in Assam and lived in Delhi. I mean, went to school in Delhi. Also been in the US for almost close to 40 years now. So and I feel like that we don't do certain things very well in our education, especially scientific education, which is that we are very kind of narrow-minded in the way we look at a problem. But as your talk today showed, it's actually many things are very interdisciplinary. Because you talk about physics, you talk about the relativity, you talk about the mathematical aspect, you got the statistical aspect and the precision aspect. You kind of the problems are actually much more complex than it appears. And that doesn't mean to suggest that you do not want to pursue something narrow to understand something well. You should do that. But at some point, there are somehow a broader sense of what it is. So when I started thinking about it, and with the pandemic, I realized that, it is possible to create a platform because people are watching it, things about, through Zoom and whatnot, they can actually join remotely. And secondly, the technology has made it very easy for me to, I was driving from Kansas City to Washington, DC. It's a 1,200 miles, about, 2,000 kilometers. And I actually conceived the whole idea during the trip that I can manage it in my mind. That was very important to me. I could not have done this 10, 15 years back, both because the technology was not there to be able to do something like Zoom and all the things I want to set it up and, and the way I wanted to be able to do it, because I also need to, it's a trade-off, right? As Priyanka, we talked about, a trade-off in my time, how much I can spend to be able to do something meaningful to me. If I spend, let's say, 10 hours a week for something and it's not coming out properly, I have to rethink the equation there on how to do it. So I felt like I could do it. And I purposefully had brought people from not very famous people necessarily. I wanted to have the mixture because I want the audience to be mostly in the context of college student, and you're teaching at the college level and stuff like that, but not necessarily in sciences. I made that point that you don't have to be in sciences, that you can see certain things about how it is connected. And there's a one driver for it, because not everybody is going to be scientists. We know that. Second thing is that science education is so important because you might be involved in science and technology policy as an officer later in your life. So you need to make a decision. Is it important to teach something about this, right? You are in the education department, and so you are not a scientist, but you need to understand that what the implication of that is. You don't always think philosophically, but those things, if we kind of incorporate that from early on, I feel like there's a overall benefit to the society. And with this, because of many of the talk, this my colleague who gave a talk a few weeks back, a couple of months back, where he does is on this medieval chance, how to actually look it through the spectroscopy on one side, and then being able to actually see if somebody edited those documents, put new musical notes and stuff like that through, signal processing and stuff. You can suddenly realize that technology is just not limited to technology. You can actually apply to see how we can understand about languages or writing over time. So I can do some frequency, whatever I can say, did Assamese writing change over the last 100 years? And how did it change? And you are going to look at a problem differently than anecdotally saying, well, somebody wrote more of this style. I can see by looking at, but that has my own internal bias. I can see that how SKC writes it versus Lakshmanath Beswara wrote it 100 years back, right? So you can bring a scientific component to analyzing even a lot of this humanities fields to be able to understand things differently. And so I have been always fascinated by this interdisciplinary way to look at things. And so I felt like that if I can do and bring in folks from, younger folks, not necessarily, I mean, older folks, but more experienced for to be speakers. So instead of just focusing, okay, something you don't want to have some speaker who is like, well, 30 years older than you. It's like, how am I going to get there in 30 years? That looks like too big of a barrier to cross. So you want to have this, and that's where bringing someone like you on the younger side is, to me, is very important. And I really liked your talk because, I mean, I know you, and I remember having dinner with you in Paris 2 years ago. But it is so fascinating the way you can explain a very complicated topic.
I think PhD teaches you that.
Not necessarily, I can tell you that, but you have been able to get there. So I really enjoyed it.
Okay. Can I have a quick word here?
Yes. Please do.
If you have a few minutes.
Sure, go ahead.
I'm really impressed with the talk. Unfortunately, I didn't see the level of participation by audience here. So I have a suggestion for Deep that when we circulate these messages, the title itself doesn't tell us whether I should participate in the talk or not. So maybe now, as a hindsight, I would say that I might have regretted not participating. The talk was so wonderful. So when we circulate the messages, maybe we can give some trailer or glimpse of it. So that's just, and in the past I have attended your webinars, and they have been impressive. They have been great, and as you said, some of them are geared towards college students, and I have seen college students participating. So that's one thing. The other thing was for Priyanka. Such an impressive talk, and
Thank you.
The amalgamation or integration of science with philosophy, it touches my heart so well. So,
I would love to talk about it.
Yes. So we can talk about philosophy ad infinitum. A couple of questions that came to my mind is, one is, now this is all human intelligence, right? That we are able to create with symbolic knowledge and add to the biological intelligence that we have. So are you going to think about intelligence in the space, the extraterrestrial intelligence kind of things? There is a search for it. So are you going to delve into that? That's one question.
I have no, okay, sorry, but ask the second one.
And the other is, these things are accelerating, right? Everything is building on top of each other. As Deep said, that we are standing on the shoulders of giants who have built all this. And we are standing and we are making progress at an accelerating pace. So things that happened just 10 years ago now, as Deep said, 10 years ago, we didn't have Zoom and all those, but things are accelerating and happening so fast. So are you looking at that also in terms of the basic philosophical questions from our Indian philosophies is, who am I, where I came from, and where am I going? Those three are the questions. And you are giving some kind of a thing here saying that here I can use equations to say, where am I within so many kilometers or nanometers finally. That's where I'm going to say. who am I and where am I really going? What's my destiny? So again, those kinds of questions will pop up. So that's getting more into philosophy from science. I'm done. Now you can talk.
So thanks. They're really interesting questions. So firstly, yes, I have no illusion that we are the only living beings in this universe. It's huge. I'm sure there's life elsewhere. It's just not, even if it's very advanced, it's like us. We've just not been able to find the right kind of signals to send.
So I might give you a reference of this book that I'm currently reading by Ray Kurzweil. He has talked about, this book is about singularity.
Mm-hmm.
And he has given a part of an encyclopedia of a lot of these things which are over my head. Actually, I haven't understood half of it. Some of it I try to understand. But the current chapter that I'm reading, he makes a point very emphatically that we are the only civilization that has intelligence in the world, because if there were intelligence in the universe somewhere else, then we would come across it in these billions of years. So it's interesting reading, but
so I don't know about that. I don't know if I agree with that.
But just a counterpoint from that book. So I don't have a stand on it. I'm a newcomer in that.
Right. I mean, if you think from a whole perspective of Big Bang Theory, if you, I hate to say the expression, believe it, that basically says that different things are moving at different time. There are probably some places in the universe it is actually very minimal intelligence. There may be in microcosm right now in terms of it. Some it has actually moved way far away. What we have not been able to connect, and this is where the signals are very important to study, is that how far can we send a signal to be able to get something, and we're still only being able to get to whatever Jupiter or whatever with our, spacecraft right now. So we're not there yet, and somebody might be trying to connect us also. They might be even much more intelligent than us, for all I know, or much less intelligent possible. We cannot say everything is going to be intelligent. So I think it's not going to happen in my lifetime. I know that, but but I cannot rule out the possibility, especially somebody was think about probability a lot of time. There's the probability and the possibility. There's definitely possibility of that out there at different forms out in the world.
Of course, one of the main things in that book is, are we immortal or not? And if we say we are mortals, why? And if we say immortal, then which part of us is immortal? Is it the body, or the integrated body with all the technologies that we have now, and so on? So it's interesting read.
It's a good question. So I would just like to add to that point where I agree with Deep. It's just that I don't think we have, it's not like fate has decided, okay, in 1919, Einstein will come up with this theory, and it just happened as we advance, as we had more people getting into science, we had, and so all this signal processing stuff, all this technology that we have, it's very recent, and it's, even despite it being recent, we've made a lot of advances, but it's still not enough. Just to give you an idea, so a lot of people are working on exoplanets. So these are planets that are not part of the solar system. They come from a different solar system, and the Milky Way has, I don't remember off the top of my head how many millions of stars, and some of them might have a solar system like ours, and some of those planets might have might support life. So something called the Goldilocks zone. What struck me was all the exoplanets that we know till date only belong to the Milky Way. We do not have the technology of pinpointing even one planet in a different galaxy, even something as close as Andromeda. We have no clue what's out there in the universe, really, if you think about it. So
that's why it's so fascinating.
Life can be just anywhere in these so many.
The book talks about the anthropic principle, and also things like the constants, the speed of light. For example, can we imagine that the speed of light may not be constant and we can do something bigger, larger than speed of light? It delves into that also.
There's a lot of interesting research on that point. Yes, like is the speed of light really the fastest thing?
And when I was reading, what crossed my mind was in Indian philosophies, we have something called Manaparya Jnana, which means you can see what's going on in somebody's mind. And of course, these mental waves. Now, are we constrained to just brain waves and figuring out what's going on in somebody's brain and then deciphering something out of that, or is there something more to it to figure out what's going on in somebody's mind? So again, that's a signaling system of its own.
Those are philosophical questions that I don't know if I can give an answer to, because I mean, if you look at every day, we have these funny incidences that we cannot explain, like a deja vu, like something which you feel like you've already seen, but you can't really pinpoint, These are things that your mind, which has so many petabytes of connections, worth of connections, just all this information in your brain that is somehow making you who you are. And but I feel like even your brain is very good at filtering out a lot of information, so you only have access to a little bit, and you might not even know your own brain, the kind of connections it makes within, and then suddenly you remember something or something. So all of that is quite philosophical to understand. Maybe eventually one day we'll be able to map our mind, but
that's going to take a while, but
yeah.
No. Yeah. Anyway, it's a very interesting conversation. Okay, but I want to, I think we need to close it, so I really want to thank you, Priyanka, for giving a fascinating talk and explaining something so easy.
Deep, are we going to have a link to the recording that I can forward to some people?
Yeah, I will have it uploaded to YouTube. All of my things are available on YouTube, Jayesh, so I'll make that available as well. So thank you again, Priyanka, for your talk, and
thank you for this opportunity, and thank you, Jayesh, for your questions.